So how do you name a billion new things every single day when they're being created all over the globe, and you have to guarantee, absolutely guarantee, that no two things ever get the same name? Well, it's not some philosophical riddle. It's one of the biggest engineering problems for any system that operates at a massive scale. Today, we're going to break down how Twitter solved it with a really elegant approach they called Snowflake. Just try to wrap your head around a platform like Twitter. Every single tweet, every like, every follow, it all needs its own unique ID. And if two tweets somehow get the same ID, well, one of them might just disappear. Poof, gone. And here's the kicker. If those IDs aren't ordered by time, your database slows to an absolute crawl trying to sort and find things. If you get this wrong, your system just can't scale. It's a hard limit. That, right there, is the billion ID problem.
So here's our game plan. First, we'll nail down what a perfect ID even looks like at this scale. Then, we'll check out the early attempts and see exactly why they failed under pressure. That's going to lead us right to the brilliant breakthrough that is Snowflake, and we will dissect it bit by bit. We'll also cover the real-world traps you have to watch out for. And finally, we'll wrap it all up with a super practical checklist you can use for your own designs.
All right, so what makes an ID good when you're dealing with this kind of volume? It's definitely not as simple as just counting up from one. The requirements are actually super strict, and they can literally make or break your entire system's performance.
Okay, so let's get specific. What do we actually need? 4 things. First, it's got to be globally unique. No collisions, not ever, not across any machine anywhere in the world. Second, it needs to be a 64-bit number. Why? Because that's compact and incredibly fast for databases to work with. Third, and this is the secret sauce for performance, the IDs have to be roughly sortable by time. And finally, the system needs massive throughput. We're talking over 10,000 IDs per second on every single machine.
So how did engineers first try to tackle this? Like any good engineering story, the path to a great solution is usually paved with a few failed attempts. Let's look at those early ideas and see the critical flaws that popped up when they hit that wall of massive scale.
The first stop for a lot of developers, and you've probably used these, is the UUID. It's built right into almost every programming language, and its whole reason for being is to be, well, universally unique. You can spin one up on any machine, anywhere, without talking to any other system, and you can be pretty darn sure it's one of a kind.
But here's the catch with UUIDs. They are fantastic for uniqueness, no doubt, but they are terrible for databases. Because they're completely random, every new ID you create gets shoved into some random spot in your database index. Over time, this just shatters your index into a million little pieces, and your read performance, it just falls off a cliff. At scale, this isn't just bad, it's a total deal breaker. All right, so if random is bad, what's the opposite? Perfectly sequential. The next logical idea is what we call a ticket server. Think of it exactly like the ticket dispenser at a deli. Every time a part of your system needs a new idea, it just goes up to the central server and says, hey, give me the next number. And the server just ticks a counter up by 1 and hands it out.
Now, this approach gets us those perfectly ordered 64-bit IDs we wanted. Awesome. But in solving that one problem, we've just created a much, much bigger one. That central server, it is now a massive single point of failure. If that machine goes down, your entire system stops writing new data. It's also a huge performance bottleneck. Every single ID request has to travel over the network, wait in line, and get a response. That one server just can't keep up with thousands of machines all asking for numbers at once.
And this is where things get really interesting. After seeing the flaws in both random UUIDs and these centralized bottlenecks, the engineers at Twitter came up with something that took the best of both worlds. They designed a system that was decentralized like a UUID, but produced nice, ordered 64-bit IDs like a ticket server, and they called it Snowflake.
This quote from the original Twitter team just nails it. They realized that to support millions of users, they needed a system that was both decentralized and time-ordered. You couldn't just pick one. The key insight was that you could sacrifice perfect sequential ordering for good enough time-based ordering, and in doing so, unlock massive, massive scale.
So how does it actually work? This is where the design is just so clever. Snowflake doesn't just generate a random number. It carefully packs 3 different pieces of information into a single 64-bit integer. Each piece has a very specific job to guarantee uniqueness and order without ever needing to talk to a central coordinator.
The first and biggest part of the ID is a 41-bit timestamp. It's literally just the number of milliseconds that have passed since a specific start date or an epoch. By putting the time right at the front, the IDs are automatically sortable. A bigger ID means it was created later. Simple as that. This is the whole key to getting that database-friendly performance we were talking about.
Okay, so the next 10 bits are for the machine ID. This is how Snowflake gets rid of that central server problem. Each one of your servers, up to 1,024 of them, gets its own unique ID number, and that number is embedded into every single identifier that machine ever creates. So even if two different machines generate an ID at the exact same millisecond, they won't collide because their machine IDs are different.
But wait, what if a single, really busy machine needs to generate multiple IDs within the same millisecond? That's where the final 12 bits come into play. It's just a simple counter that resets every millisecond. The first ID in a millisecond gets a sequence of 0. The next one gets a 1, then a 2, and so on, all the way up to 4,095. This lets each machine handle incredible bursts of traffic with ease.
So when you put it all together, you get this beautiful 64-bit structure. The first bit is just left unused. Then you have the big timestamp chunk for ordering, the machine ID for decentralization, and the little sequence number for handling high-speed bursts. These three parts work together perfectly to create a globally unique, time-sortable ID without a single central point of failure. It's honestly just a brilliant piece of engineering. Of course, no design is a silver bullet. Moving to a time-based system like this introduces its own set of challenges, especially when you're dealing with something as tricky as clocks across thousands of computers. These are the dragons you really have to slay to get this right in production.
The biggest, scariest danger is clock drift. See, your server's clock isn't perfect. To keep it accurate, it periodically syncs up with a time server using a thing called Network Time Protocol, or NTP. But look at this timeline. What happens if your server's clock is running a little bit fast? When it syncs with NTP, it might have to turn its clock backwards by a few milliseconds. If that happens while you're generating IDs, you could generate an ID that is smaller than one you just made. This breaks the ordering guarantee, and even worse, could create a duplicate. This is a critical failure you have to handle.
And then there's the classic race condition. Imagine two requests hitting your server at the exact same time. They both read the current sequence counter, which is, say, 3. They both add 1 to it in their heads, getting 4, and then they both try to write 4 back. Uh-oh, you just handed out the same exact ID twice. To stop this, you need what's called an atomic operation, which is just a fancy way of telling the computer, hey, this whole process of read, add, and write, it has to happen as one single, uninterruptible step.
So with all of that in mind, how do you know if a Snowflake-style idea is the right move for your project? Let's wrap this all up with a really practical design checklist you can actually use.
Okay, here's your 4-step framework. First, ask yourself, is time ordering absolutely critical? If you just need a unique number and you don't care about database index performance, a simple UUID might be way easier. Second, what does your traffic look like? Could you ever generate more than about 4,000 records in a single millisecond on one machine? If so, you might need to tweak the design. Third, you need a solid plan for managing machine IDs. How does a new server get its ID? And how do you make sure you never reuse an ID from a server that's been shut down? And finally, and this one is non-negotiable, you must have a strict plan for clock synchronization. If you can't be sure your clocks are always moving forward, this whole approach falls apart.
And that really brings us to the final question you should be asking yourself. As your system grows from thousands of users to millions, the tiny design decisions you make at the very core, right down to how you identify a single row of data, they become either the foundation for your success or the bottleneck that holds you back. So are your IDs built for the future?